Yeah. So my name's David, or David Nadlinger. I'm currently a student at the Swiss Federal Institute of Technology in Zurich. My online handle on ClickForBoats, Twitter, on GitHub, Twitter and so on is ClickForBoats. Today I'm going to talk about LDC. So just to get a general idea, who of you has like a good idea what LDC is supposed to be? Oh, that's most actually. And who of you have actually like used LDC, downloaded the binaries, or played around with the GitHub sources? Oh, still just about a third of the people. So well then, LDC is obviously an acronym for LLVM-based DConf. What is this talk going to be about? At first, I'll try to give you like some kind of executive summary about LLVM in general, why we as a D community or programming language community should be interested in it. I'll then give a brief recap of the history of LDC and of course ending with where we are now, because this is arguably the most interesting stuff for most of you. In the second half, I'll give you a quick tour of the internals, like describe the general high-level architecture, go a bit into our development process, hopefully get new people to work on LDC, and close with a few remarks on where we are going, what the most interesting opportunities are, and what the biggest challenges are for LDC. So, one last thing, if you have questions, please feel free to interrupt me at any time. There will be some minutes, I hope, for questions at the end, though, so you can wait for that as well. This is LLVM, or to be precise, the LLVM logo. It is probably inspired by the Dragon book, like the compiler construction textbook. So obviously, LLVM has something to do with compilers. And in fact, it's what they describe as a compiler infrastructure. And this is to say that LLVM allows you as a programming language compiler writer to reuse many language-independent parts. So just to be clear, LLVM is actually much more than just the LLVM core libraries right now. So we are talking just about the core, but there's also Clang, which is a C compiler. Okay, yeah. Heard about it. Clang is a C compiler. There is LLDB, which is the debugger built on some Okay, so the point is that LLVM is the LLVM project, and in the LLVM project, alongside Clang and LLDB and other checking tools, runtime libraries, there's the LLVM core libraries. And those core libraries are really just, or started out at least, as a way to generate code and generate code, but we are not using the just-in-time compiler in LDC. Generate code for quite a number of backends. There is x86, there is ARM, there's PowerPC, MIPS. There's even some backends for the shader intermediate representations used by NVIDIA and AMD. There is some of more exotic backends, like backends for certain DSPs, and of course some experimental stuff like compiling LLVM to JavaScript. So this is certainly one of the points to use LLVM. We have many targets. Also, it has a pretty much a state-of-the-art optimizer. It's on par with GDC, depending on which benchmark you look at. It's like plus or minus a few percent here and there, but it's pretty much in the same ballpark. What's also great about LLVM is that although it started out as a research project at the University of Illinois at Urbana-Champaign, it has actually gained quite a lot of adoption in the industry. Apple, of course, is really pushing it. It's the main compiler, so Clang, based on LLVM, for both OS X and iOS, but also Intel, NVIDIA, AMD have engineers working on it, or at least the parts of it that are interesting to them. Google is actually using it in some way or form, at least as far as I'm informed. And there are many, many other big and smaller companies using it. So it's a huge ecosystem by now, and it's not going to die anytime soon. And one last important point about LLVM is that it's actually open source. And very liberally so. So it's under a BSD-like license, the Urbana-Champaign University or whatever license. So you can actually use it in commercial projects without like having to open source your source. So it's not pirate at all. It's BSD-like, I guess you're all familiar with that. So the question is obviously, how can we use this great project for DE? How can we take advantage of it? And if you're asking this yourself right now, you're actually not the first person to do this. So actually, LLVM was released back in, well, the first like 1.0 release was back in 2003. And pretty much immediately after that, people started posting like on the D news groups, hey, there's this new project I've heard about. Can we use it somehow? And in 2004, there have been some like first experiments. I think it was Resistor, I think Owen Anderson, playing around with it and experimenting here and there a bit, asking for advice on how to integrate the DMD front end with it. But those experiments haven't really gone anywhere as far as I'm aware, and it wasn't until like mid-2006 that Thomas and Chris Olsen posted on the D news groups about his take on using LLVM for D, which is the LLVM DC project, which was later renamed to LDC. So we are a direct like successor of LLVM DC. And if you actually look at the source tree of LLVM, of LDC, we're actually using Git right now, but back then it was SVN. The first commit was like in the middle of 2007. So back then, obviously, it was quite a rudimentary state still, but at the Tango conference 2008 in Torun in Poland, it was actually at a point where they said like, yeah, D1 support is pretty much finished. There are some rough edges here and there, but we are pretty much in a good shape. So they went on to like work on the source, clean up some of those issues, and actually released the first version of LDC. So they had renamed it to LDC at that time in early 2009. So work continued to go on that. Unfortunately, like in the middle of 2010, Christian Kamm, who had been a major force in the development of LDC as well, and Thomas and Chris Olsen really both more or less left the D community, or at least weren't active any longer on the like compiler development side of things. But at the same time, Alexei Ibrokin started to push forward on getting D2 supports done in LDC. So there was some initial support of D2 at that time, but it was really like incomplete. Tests didn't pass, the frontend was outdated, and so on. So this continued, and in 2011, we actually moved to GitHub. And shortly after that, in November, D2 support was in a state where we actually declared it the default version of the compiler that was built if you just invoke like CMake with no additional flags. So there was another year of like intensive working on getting things into shape. But finally, just before last Christmas, we were able to release LDC 0.10, which was the first release to like officially support D2, the first release to officially like be at the latest D front end, and more or less the first usable D2 compiler based on LLVM. So much for the history lesson. Where we are now. So actually, I wanted to push out beta before the conference because it obviously would have been interesting for you guys to just being able to like download the binary packages, but unfortunately I couldn't manage to. But in Git master, we are at DMD 2062, which is the latest release. On Linux and OS X, on both 32 and 64-bit x86 platforms, it pretty much just works. Everything passes, except for very few cases, which I'll go into shortly. But let's first have a look at the other platforms. So as I said, x86 is pretty much rock solid. That's our main target. PowerPC is also an interesting target. The standard library compiles there, but there are still some issues, like with the test suite not passing, some rather hairy details here and there. And actually, the guy who has been doing all the work on PowerPC is here as well. That's Kai, if you maybe can stand up for it. So Kai has been doing all the work on PowerPC and also on Win64. So if you have any questions regarding that, he is the best man for them. And of course, there's ARM. ARM is on all the embedded devices, and we would be really glad to have a working decompiler for ARM. But unfortunately, it's not quite there yet as far as LDC is concerned. So the slide actually should have been updated a bit, right? Before the conference, I was able to get Hello World to pass, like the Hello World with. But wait a second. It's only on ARM Linux, and it's a huge hack, and it doesn't really support the ARM eABI yet, and so on. So there's still a long way to an actually usable compiler. And the stuff is not even in Git yet because it's a huge mess. So I just wanted to get it done, so I got it done. So, but there is light at the end of the tunnel, certainly. Linux, of course, is pretty much the main development platform for any open source project these days. And LDC pretty much works flawlessly on Linux. On OS X, the story is pretty much the same. We do require OS X 10.7 Plus, though. So Snow Leopard unfortunately doesn't work. The reason for this is that we actually rely on the thread local storage support in LLVM, which in turn relies on OS X's thread local storage, which wasn't added until 10.7. So that's definitely something to keep in mind. On Windows, the story, well, it has historically been a long story for LDC. The main problem has been exception handling all the time. So on x86 Windows, 32-bit Windows, the mechanism used by the operating system and also by DMD is called structured exception handling. And it turns out that SEH is covered by some patents owned by Borland, which are due to expire in 2014. But until then, the GCC and LLVM people both said, now we won't take the risk of accepting that into our source tree. So for a long time, there was no exception support in LDC for Windows at all. But recently, LLVM gained support for doing dwarf-style exceptions. This is the kind of exception handling done on Linux, even on Windows as well. So it's not a platform-native exception handling mechanism, but it works using the MinGW runtime. So actually, I had to do some fixes to the thread local storage support in MinGW and LLVM on MinGW as well. But they are upstreamed by now. And if you're using LLVM 3.2, there's a wiki page describing on what patches you have to apply to build it there. If you are using LLVM trunk and MinGW W64 trunk, then it should pretty much work out of the box. We are definitely going to release a alpha quality release as part of the next official DMD release, LDC release, because the only remaining issues on Windows are really COM libraries, some symbols in some COM libraries which are used in the test suite not being found. That's definitely something we can solve. Win64 is a similar story in as far as exception handling goes, because it's a completely different mechanism, and it actually is possible to implement it without infringing on any patents. But Kai has been doing some work on this, and it almost works, but there are still some hairy API issues. So it's probably like a week of focused work of getting it done, I'd estimate. But yeah, we are still not quite there yet. Yeah?
Is most of the work just making it compatible with existing C++ code on the platform? Repeat.
The question was if most of the work is making it compatible with existing C and C++ code. And the answer is, in this case, no. We really just have to, if you're porting T to a new platform, you basically have to get exception support done. You have to get GC and TLS support done. Otherwise, T is not usable. And the issue really is generating the right exception handling tables and so on. C and C++ code after that is pretty much, that's the stuff that's supposed to work anyway. Linking to C is not hard. Getting the OS level details right in exception handling is. So, yeah. Okay. There are other operating systems, of course. There are all the BSD variants. people have used LDC on FreeBSD and OpenBSD, but it's not regularly tested. Maybe we can work out something there. Yeah, and Android is obviously interesting for mobile development. The issue is that although Android is based on Linux as a kernel, they use a different user lens. They don't use the GNU's libc, but Bionic, which is a slimmed down version of a C runtime library, and some of the functionality, including I think TLS support, thread local storage, is not quite there in this platform. So it definitely needs some work. And people have also tried to use LDC on AEX, Haiku, and some other rather exotic platforms. It might work. So LLVM does support a few dozen or more of, platforms, but yeah, there is a runtime support necessary, and it should be possible to get LDC to work there with a fairly minimal amount of work, but we're not officially supporting it in any way. So, language support. Now we're coming back to the almost in parents before. There are a few things not implemented yet, one of which is exception chaining. So how many people here are familiar with exception chaining? Oh, that's just about half the people. So I guess I'll shortly explain it. The situation where exception chaining occurs in D is when you have a scope, for example, a try finally block, or just a struct on a stack, and you somehow leave this scope, and in leaving this scope and cleaning up all what you had there, for example, like structs with destructors or finally blocks, you throw another exception, even though there already is an exception in flight. And indeed, there are two things that can happen now. If there is an exception, like with capital E in flight, and you throw an error, the exception is replaced by the error, because an error is more severe. And in all other cases, more or less, the exception object is just changed to the end of a linked list starting at the in-flight exception. And the issue is there that we are compared to DMD, not actually using some custom unwinding mechanism, but the same unwinding mechanism as GCC does for C++, which is a library called libunwind. And it is possible, or at least I think it should be possible, to implement those advanced features using libunwind, but it's a rather hairy mess. You have to sit down and look at the exception handling tables. I tried to do it over a weekend and couldn't do it, so it would probably be a week's amount of work to get this done, like a week of spare time work, mind you. And it would probably benefit GDC as well, though. So it might be an interesting thing to look into. Then there is some restrictions on the inline assembly. So we do support DMD-style inline assembly, unlike GDC, but LLVM, or at least the way we currently implement inline assembly on LLVM, requires you to not change the control flow from inside inline assembly. So what you can't do is go into inline assembly blocks, which is supported by the language spec. There doesn't seem to be a lot of code around which actually does it, like jumping to labels in an assembly block, but there are tests. So jumping out of an inline assembly block actually works. We have a workaround for that. So basically, you get one extra conditional jump, unfortunately, but there's no way around. Then there is a few of smaller issues, like LLVM is a typed system. I'll go into that later. And you can't do things like declare two functions with the same mangled name, but a different type signature. And obviously the question is, why would you want to do this? I'm not sure, but the runtime does it in a few places to hide implementation details, and for example in the array or as associative array handling code, and it's usually easy to fix, but something to be aware of. And as far as language goes, there is also a few extensions to what DMD offers. There is a few pragmas, which allow you to, for example, mark a function which contains inline assembly as being inlineable. So usually you have to disable the inline of a functions containing inline assembly, but you can mark it up as, yeah, that's possible. On the other hand, you can also disable inlining You have access to LLVM intrinsics or GCC style intrinsics, but it's mostly like small features here and there. One other thing which Manu is going to talk about in a few minutes is SIMD, and LLVM, or rather LDC, actually supports SIMD. The SIMD types only though. So I don't know how many of you are familiar with this area of D, but there's this magic __ vector type, which is used to implement the types in core.simd. And we support this, so we support vector types. But DMD also supports the __ SIMD intrinsic, which actually allows you to directly specify the x86 opcodes used to operate on the vectors more or less. And we don't do those because it would require us to back translate the x86 instructions into a target independent form, and there are better ways to do this on LLVM. But that's mostly minor issues. And actually, stits.simd is going to fix this, at least if Manu gets to implement his plans.
What are you trying to say?
I once did the SIMD. That's what I'm trying to say. Anyway, so DMD compatibility. There is LDMD2, which is a tool you can use as a drop-in replacement for DMD. So it has all the same command line switches. You can just transparently replace DMD with LDC in the build systems. It does support steps and other switches required for working with RDMD. Coverage and profile info generation are not available though. I mean, I see Walter's point in making it as easy as possible to use for users, but there is quite a few external tools for that. So you can do coverage analysis and profiling with LDC as well. It's the same as for GDC. As far as ABI and link time compatibility of DMD and LDC sources goes, linking together one object file produced by LDC and another object file produced by DMD, we generally try to be as compatible as reasonably possible, but unfortunately we are still not quite there, and this includes all three of the compilers. We have to have a talk about this at some point, but it's a rather messy affair, and if you're interested in the details, you can contact me afterwards. So, one of the selling points of LLVM, at least of those I presented here, was its optimizer. And the question obviously is now, how good is it? And to do this, I decided to steal a slide from Andre, more specifically from his talk at lang.next 2012, which was at Microsoft, where he talked about the expressive power of D and how D allows you to do things which other languages don't. For example, he chose this benchmark from the computer language benchmarks game, regex DNA, which just matches a couple of regular expressions onto a data set consisting of DNA information, a few megabytes. And what Andre did there is benchmark the times, run times for the different implementations. So what is it? Yeah?
Wasn't me. Dimitri did all the benchmarking.
Ah, okay. So, okay, yeah, the numbers are from him. But I got similar numbers, and those are my numbers anyway, so yeah, they should be sound. It's Java util regex boost expressive thread. That's the new std regex in the DE standard library. Google's RE2, V8, and std.regex again, but the compile time version, right? The automaton is generated at compile time using CTFE. And Andre's point was, obviously, Dmitry was just a student who wrote this over the course of a single summer, and he beat almost everybody besides RE2 and V8, and the compile time version beats everybody on the planet. Well, it turns out that those benchmarks have been done, not by you, but with Dmitry, using DMD. And if for those benchmarks actually LDC or GDC were used, the graph would have looked something like this. So suddenly, well, you really have to clap for the LLVM and GCC people here. But the point is that actually suddenly Dmitry is beating everybody instead, except for V8. And the reason why he doesn't beat V8 is that V8 actually JIT compiles the VM used for regular expression matching. So it really should be compared to this column and not to the runtime version. Sorry?
What is the y-axis?
The y-axis is, I went with Andre's slide there. It's like relative speed. So it's the execution time normalized to V8, which is the fastest non-D implementation around.
Higher numbers are better.
Higher numbers are better. Yeah. Sorry, it can't be the execution time then. Yeah, it has to be throughput. Because, yeah, the next slide is higher numbers are better. And so I went on to do a few more comparisons to like give you a general idea of where the different compilers are. So the first two columns are what we already saw with DMD in yellow. So this time normalized to DMD, and with the relative execution time, this is lower is better. The green column is LDC 0.11, which didn't quite make it out for the conference. And so it's just the latest Git master and some very recent Git build of GDC. So those numbers are sound, but I didn't even bother to put like error bars on them because I'm not trying to do like real benchmarking here. I'm just trying to give you like a general feeling of what to expect from a different decompilers. We also have D-ray tracing here, which is a simple ray tracer written. So I didn't choose those benchmarks in any specific way. I just wrote a post on a news group saying, hey, I'm doing this talk on LDC, give me some benchmarks to present. And this is what people came up with. So it's a simple ray tracer in D. It's fast Fourier transform written in D by Jonathan Pfau. It would be interesting to see why GDC beats LDC here by a factor of, I don't know how much, but pretty significant. We definitely have to look into this, but both LDC and GDC enjoy like custom code here, so I'm not sure what's going on there. So he actually wrote 3 versions of it for DMD, LDC, and GDC, as far as I'm aware. And there's also Joseph Wakeling's DREX, which is, as far as I understand, mainly linear algebra as well. Yeah, Ian.
All right. Just out of curiosity, what optimizations have you got turned on for those benchmarks?
I've honestly tried to make each compiler as fast as I could, which means like O release inline no bounds check for DMD, O3 and enabling the vectorizer for GCC, and release of course in the others, and the same for LDC. So that's the best. Even I think in some cases I didn't take the O3 numbers because they were lower than the O2 numbers, so I tried to get the best results of each. So it's not scientific at all. That's what I was saying. So, yeah, it's actually it has been run on a Core i7 dual-core processor, if that's interesting as well. So, other benchmarks are, and this is another area where actually Dmitri's work really shines, is his replacement for std.uni, which is to make its way into Phobos shortly, at least if review goes smooth. And what this benchmark does here is to basically read in a file of all the page titles from the German Wikipedia, German because it contains more interesting Unicode characters than the English one does, and classify each character based on if it's an alphanumeric character, marking character number, symbol, white space, and determining the combining class. And what you see here is that actually DMD can do if statements. There is no performance problem with if statements in DMD, because in these columns here, actually the early exit is hit pretty often because most characters are actually alphanumeric characters or white space. There's a fast path for ASCII in there. And for the others, there is a three-level try lookup, and DMD quite well fails to inline some of the lookup and spills some registers to the stack and so on, while LDC and GDC optimize the benchmark down to a tight loop, and yeah, this is why we get some really ludicrous, like 10x speed up here. Anyway, some more benchmarks. That's a library I wrote, Thrift. It's used at Facebook for, well, I obviously wrote the D implementation for it, not the whole Thrift library. It's used at Facebook for for their service-based architecture, at least in parts, for communicating between different servers. And what this benchmark measures is really just serializing out of a memory buffer and into a memory buffer. And what I really want you to look at is the fact that pretty much everything is below 70% there. So it's a 30% speed up here as well. So why I'm making, yeah, sorry. I'd rather not talk about this. Yeah.
Please talk about this.
No, it's a crash when I tried to compile the test.
Repeat question.
No, the question was what happened to GDC, and I couldn't get it to compile the test. So didn't want to make a huge point of that, so yeah. Why am I talking about this anyway? I mean, 30% is certainly a lot if you're doing like really performance-intensive stuff, but why does it merit like 3 minutes in the talk? Well, the reason I believe it is central to D to have like performant compilers is that if we step back a bit, it's actually control that drives us towards using system languages instead of like Java, C#, or even Python or Ruby and so on. So the question is, why do we want control? Because we have ultimate control out down to the byte level, down to the instruction encoding level, what happens with our code. But why do we want it in the first place? Well, if we're not writing device drivers, and most people aren't writing device drivers most of the time, we do it because of performance reasons, or performance requirements, really. Because if we have this kind of control, and if we know the machine we are targeting, and if we can exploit the specifics of the targets, then we can actually get some really nice speed-ups. But, I mean, if control gives us speed-up, why don't we write anything and everything in assembly? Because assembly is the ultimate control tool. Well, it turns out that actually the human brain is limited, and you need to introduce some kind of abstractions to be able to like handle mentally any reasonably complex program, not even taking into account the debate of whether you can actually beat compilers at handwriting assembly these days. So we need to introduce abstractions, but we can't really afford to like pay a lot for those abstractions, because then the added control, the benefits of the added control would disappear. So what we really need is zero-cost abstractions. And for this to actually work out in practice, we need to have good support for compiler optimizations. The compiler needs to be able to inline away all those fancy templated method calls and so on. It needs to be able to devirtualize stuff when it's not actually virtual and so on. And so my point is that we need good optimizing decompilers, because otherwise people are not going to be able to take advantage of the features that make D expressive, at least in a certain context. So any questions so far? Well then, let's move on to the internal architecture of LDC. So what we see here is a D source file in the top left corner. And making its way through the compiler, it actually gets passed and analyzed first by the DMD frontend. Then the LDC glue code is going to generate LLVM intermediate representation of that. I'll get into what LLVM IR looks like in a second. And either we can dump it to disk or in a binary or a textual format for later use, or in the most common case, it gets passed along to the LLVM optimizer. And it's just the normal LLVM optimization passes which do transformations on the LLVM IR level, extended with a couple of not very significant, to be honest, D-specific passes. So we have stuff in there like promoting GC allocations to the stack and so on. But the cases where those language-specific optimizations kick in are really few and far apart, at least in our test so far. Anyway, after the LLVM intermediate representation has been optimized, it gets passed along to the LLVM code generation in the bottom left corner there. And the LLVM code generator generates the machine code for the target language, either directly in the form of object files or textual assembly files, which then can be assembled using the GNU assembler. So the default assembly syntax LLVM uses is the GNU one. And after that, we just invoke the system linker to either generate an executable, a shared library, or of course the system librarian to, oh, that should have been A here, to generate a library. So one thing I want to highlight here is this blue box. This is just meant to tell you what actually happens in the LDC process, and what doesn't happen in the LDC process is just the linking after the object files have been produced. We invoke the system linker there. So what does the LLVM IR look like? Just to give you a general feel for what you're talking about here. So this is a simple add function, which you may recognize from Ian's talk. What we generate out of that is a intermediate representation, the LLVM intermediate representation. There's really only this one, at least on the front-end side, which is in a single static assignment form, which means that basically every value is synonymous with the instruction that generated it. You can't have any variables. This is the case. This is the reason why we actually explicitly allocate A and B as stack variables here, because in D you can obviously modify your parameters or take the addresses. So what we do here, because we don't know if we are going to end up needing like the addresses or needing to modify the variables, we store them in there. Then we load them again, add them together, and return it. And after the LLVM optimizer has a go at it, even at the lowest optimization level, it obviously recognizes that those copies and those stack slots even are unnecessary and produces this optimized IR. So really all that's left is this add instruction and the returning of temporary. Also note that there are two attributes here, no unwind and read none. They're more or less synonymous to these pure and no throw, but unfortunately slightly different in the exact semantics, but that's a topic for another talk. And from this, if we run it through the code generator, we just get the usual machine codes, in this case x86-64. So I guess you all know how this works. Right, so how is the intermediate representation produced? As I said, we actually use the DMD frontend and extend it with some custom glue code to generate the IR. And we actually have a copy of it in the LDC tree. There are some slight modifications. We generally try to avoid those because it, of course, makes merging harder, but there are, unfortunately. And there is a couple of things, though, which we don't use from the front end. It is things like some parts of constant folding and AST-based inlining, because they actually make life harder for us. And LLVM beats the DMD AST-based inliner anyway. So I promised some experience reports on working with the DMD frontend. So Walter, look away. What is really hard for me was actually getting started with the DMD frontend, because there's a virtually total lack of documentation. There are a few comments here and there. And also it's really not easy to work on DMD without having a complete picture of the system. So I've worked quite a bit with DMD now, and I find it to be like quite beautiful once you know the complete picture, but you can't really work on any part of the system with only partial knowledge without having to fear to break something somewhere else. And having to work on on LLVM or Clang or so to fix bugs there was a much more enjoyable experience in my opinion. So I don't know what we can do to improve this. And there is certain things though which we can improve, and that's some layering violations. Yeah, sorry.
I know how we're going to improve it. We're going to rewrite it in D.
Yeah, this would be an interesting project. It will definitely be, and it's also on my interesting outlooks for the future slides. So. a few like really details here. There are a few layering violations where like the front end uses stuff from the back end, such as in struct literal expressions where backend symbols are used in constant folding, which is a problem for us in LDC because we can't really do those things easily. There is also this kind of latent impedance mismatch between the DMD front end producing types that are not always the same for the same value all the time, and LLVM applying pretty much strict type information, but yeah, we'll have to live with that. So let me just go quickly about the advantages of using LLVM, like from a programmer point of view. What I found nice about it is that it is reasonably easy to approach. It's all more or less well documented, written in an interesting new style of C++. I guess they call it a tasteful subset of C++. It's rather defensively written code, so if you mess up your LLVM IR, you're getting an assert telling you what's wrong and not some crash down the road somewhere. They have pretty useful debugging facilities, such as the ability to dump pretty much everything into a graph-based form using dot and GraphWiz. There is also dump on the GDB command line, which is pretty useful because you can at any point get a representation of the code which you have already generated and things like that. There's tools like bugpoint, which allow you to reduce codes which crashes LLVM or which leads to misoptimization. So it has been really useful in tracking those errors down. It's also quite easy to extend. For example, it was no problem at all doing custom optimization passes. But aside from the technical things, one of the main advantages is also that the community is really active and really helpful. So you can pop into IRC at any time or ask at the mailing list at any time and get, usually within a very short amount of time, back a very useful answer. And patches are also reasonably easy to upstream. There isn't this kind of, nah, outsider, we don't want your stuff attitudes, which might or might not exist or might have existed in other backend projects. Anyway, some of the challenges though, the LLVM IR is not really target independent. And I don't mean like true target independence here, because obviously if you have a systems language, your IR, the IR you generate from it is always going to be target dependent, right? Like the function signatures of the OS APIs, there's probably going to be some API differences as well, and so on. But what LLVM does is leaking AVI details into the IR in a to a much higher degree than would be necessary. For example, you pretty much have to implement the APIs for, if you're doing like a C compiler or a compiler that's compatible with C, you pretty much have to implement the APIs for C on x86-64 Linux or POSIX and x86-64 Windows and all the different platforms yourself, again, because they didn't really encapsulate this well. They're also quite liberal in C++ API changes. This is usually not so much a problem if you're just going from release to release, because they only make reasonably like self-contained breaking changes if they can avoid making bigger changes. But it can be somewhat of a pain if you're like tracking SVN trunk and your code stops compiling every 2 days. There also is no emulation for missing OS functionality. That's the point I mentioned about OS X. So there is no TLS support in OS X pre-Lion, and LLVM also doesn't emulate it there. GCC has taken pretty much the opposite approach of like defining a subset of things that should work everywhere and then going great lengths to ensure they actually do. So this is not really a downside because you know what you'll get, but something to keep in mind. And the big companies using LLVM don't really care much for Windows support. So it's pretty much an open source, volunteer-only effort in these areas, and it definitely shows because Windows support is definitely lacking compared to the other parts. Anyway, so to just give you a quick overview of what the project is in terms of size, the front end is just about 100,000 lines of code. Our glue code is something like 33K, and then there is another 4K of like driver code because it can actually use LDC as a library if you want to like JIT decode. So it's not very flexible, but you can do it. And there is also another 3K of miscellaneous helper for different things. Anyway, the runtime, so this is D runtime and Phobos, is included in the form of Git submodules. So this is on one hand a boon because it makes keeping a consistent state really easy. So for example, if you're Git bisecting something, you can really just go to the Git commit and type in Git submodule update, and you know you'll get something that compiles without having to like fiddle around with the different versions. On the other hand, merging is harder. Even if you know what you're doing with Git, getting patches from somebody else who has been working on a different branch and having to merge the submodules together is not easy. We also have the DMD test suite as a submodule. I extracted it from the main DMD repository, and it's available on GitHub as well. The changes we do to the runtime and Phobos are mostly to implement compiler system-specific stuff, like implementing atomics, math, and bit operation intrinsics, which are obviously depending on the backend. Some platform support things like for TLS, GC, and so on. And there is this one difference regarding variadic arguments, where we are in the same camp as GDC in not mapping the VA underscore list type to void star, but to actually the C type because it is required. Anyway, this is a small detail. So as far as the committers go, the original authors, as I said, were Thomas Inquist Olsen and Christian Kamm. They are still like going by commit counts the biggest contributors to LDC. Alexei Prokin has been doing most of the initial D2 work. Sadly, is pretty much inactive those days. Kai is definitely underrepresented in this graph because he has done lots of painstaking LLVM work, which doesn't at all show up here. So big shout out to him. And a ton of other contributors. Fritz von Bommel has been doing a lot of work back in the days on custom optimization passes, generating more efficient code. And there's all those people whose names I can't really read out loud now. And also really quite a few people who contributed like 1 or 2 or 3 patches on GitHub. And since D as a whole and LDC in particular is a completely volunteer-based open source effort, we really need those contributors, and we're really thankful for their work. So maybe. Anyway, so just to wrap it up, development happens on GitHub. There is a GitHub organization called LDC Developers. You'll find the compiler, the runtime, Phobos, and so on repositories there. We have actually 2 CI systems now, and it's probably going to be 3 soon. Right now we're using Travis CI, which is a free service and offers Linux-based VMs for CI testing. It's well integrated with GitHub. It's definitely worth a look. You can also do D projects on Travis if you just set up the dependencies as Debian packages and pull them in. Alex Ronne-Petersen has been running the test suite on the Dykes Foundation test servers. Big thanks to Alex as well. Forums and mailing lists are on the official D forums. It's digitalmars.d.ldc. We have developer and also user documentation on the wiki. You can find pretty much everything you need there. So at this point, the question is obviously, where are we going from here? The next steps are pretty much shared library support. It's where everybody is excited about it right now. And for a long time, in the D1 days, LDC actually had usable shared library support. The issue is just that it doesn't really support the interaction of TLS and garbage collection at all. So it's currently not usable with D2. But Martin has been doing a lot of work, as he's been presenting yesterday, on those things, and I'm confident that we can fix it in the near future. Exception chaining, as I mentioned, and the x86 VARG API, these are 2 issues that really should be fixed because they affect a small percentage of users, but make our language support somewhat incomplete. We really can't say we are a rock-solid decompiler without having those 2 things done. And of course, there's the issue of minimizing differences to the DMD upstream source. and a possible translation to D. Because even though we are nowadays trying to minimize the differences we introduce in the shared source with DMD, there has been a time where there was pretty much no other option. Because if you look at this timeline again, the the DMD SVN repository was actually set up somewhere around here. The first commit by Walter was in September 2008. So by this time, LDC had been around quite a while. And it was pretty much, well, I guess I shouldn't say it was impossible to get patches back into DMD, but it was definitely harder to collaborate on shared source in those days. Anyway, so as far as future directions go, interesting goals, there is obviously the question of compiler performance itself, because I just talked about the performance of the reduced code before. And even though Kai has been doing a little bit of work here and there recently, nobody has really had a look at that so far with LDC, and it could definitely be made faster without much effort. There are like things like debug strings being generated all the time, regardless of whether they are actually used or not, and some low-hanging fruit there. And what we could also do is further leverage the specific attributes like pure, no-throw, and so on for optimization. But as I was talking to Walter 2 days ago, there's not really a clean mapping, because no-throw functions can throw, and there are ways to work around other restrictions as well. So it mightn't be easy to get a huge benefit out of this. Looking more into the what other interesting projects there are side of things, it would be very interesting to integrate LDC with some of the LLVM-based tools for program verification out there. For example, there is Address Sanitizer and Thread Sanitizer, which are developed by Google. And so they are mostly just memory correctness and thread race condition correctness checkers. D might not need them to the extent that C++ does need them because of no sharing by default and things like that. But still, it would be interesting what kind of tooling support we can offer for D here. There is also the question of link time optimization. It is possible in LDC right now, but you have to do it manually fiddling around with the LLVM commands. And of course, there are a ton of other projects based on LLVM, like Pinnacle, Mscripten, and so on, which are based on, or which try to bring LLVM-based stuff to the web. So Pinnacle is an effort by Google to make native code run on browsers, for example, Chromium. And Mscripten translates LLVM IR to JavaScript. And there actually have been some people experimenting with Mscripten in the past. So there was a news group post a few weeks ago. And it is possible, but it will be interesting to see if we can get a benefit out of it, or if it remains just an interesting experiment. And also, if we are doing cross-compilation, we would need some kind of support for setting up our tool chains, because setting up a cross-compilation tool chain is really tiresome in many ways. So, to summarize, LDC is a D2 compiler only right now, so I didn't mention it, but the 010 release was the last release to support D1. It's ready on Linux and OS X. You pretty much don't have to expect any major trouble there. Windows is coming, so there has been some recent improvements. In many cases, it produces significantly faster codes than DMD, which can be interesting for release builds. There are many opportunities, which are just a week of experimenting away, at least for getting a prototype. So it is definitely an interesting thing to hack on. And it is fully open source, so we can actually ship it with Fedora, Debian, and the other more restrictive Linux distributions. So one last thing, LDC does need your help. You could help by fixing bugs on GitHub. There is a tracker which tracks specifically junior jobs, so getting started with it. We desperately need people who champion new platforms, because LLVM supports quite a diverse set of platforms, but not really, well, I mean, Kai has been working on some. I have had a short look into ARM, but it would be great if somebody would step up and say, hey, I want to get support done. What can I do and how can you help me? We'd definitely love to work with you. You can package LDC for your favorite distribution. It's not really a lot of work, but you have to really pretty much use the distribution you are targeting to be able to know the conventions. Debian is a great missing thing here. So we actually do have packages in Fedora, thanks to Jonathan Mercier there. And we do have packages in Arch Linux. I think Sven-Henrik Hasse has been maintaining those. But there is more to do in this front. You can tell, obviously, what's really required for D as a whole is like improving our documentation, and LDC is no exception there. We would love to have help with keeping the installation instructions, getting started guides up to date. They're all on the wiki. And of course, you can help by just trying LDC on your own project, report any bugs you may find, and thus help in making LDC a more stable compiler. So who of you have actually used Dustmite or know what Dustmite is? So a huge shout out to Vladimir. It's been such a great tool and has been a huge time saver for compiler development. Anyway, that's it. One more thing, wishlist. This is actually being solved. Thanks a lot, Brad, for that. We could do this is more or less really just an idea at this point, a compiler performance tracker, compiler performance as well as runtime performance, because if you don't test it, it's broken, and we certainly don't have a good grasp on the decompiler and the runtime and those kinds of performance issues right now. And it would also be interesting to see more real benchmarks for D, because some of the more advanced optimizations we do, like promoting garbage collected memory to the stack, don't really kick in any of those micro benchmarks you saw before, because they have been optimized to hell anyway. So with that, thanks a lot for listening. The official homepage of LDC is on the D wiki. You can find us all on the D forums as well, and occasionally we are on Freenode as well in the Pound LDC IRC channel. With that, I'm going to thank you for your attention again, and if there are no further questions, I think we have like 1 minute and 30 seconds per question right now.
Yep, time for a couple of questions. No, I'm going. I got it.
Yeah. I know you have some specific paths that you implemented for LLVM for LDC to promote, for instance, call to the GC, to remove call to GC. Can you talk about that a little?
Well, what it actually does is just escape analysis on, so if you do new in D, it gets more or less translated to a runtime call, which then allocates the GC memory and initializes it. What we do is recognizing those calls on the IR level, figuring out whether the pointer they return or that is passed to them can be escaped. And if this pointer can't be escaped, and if it's below a certain size threshold, which of course entails that we need to know the size of the allocation at compile time, then we can just promote it into an LLVM allocer. There's really not much magic going on there. It is rather tricky to do in practice because you have to be careful with like loops assigning to the same pointer over and over again, but it's mostly straightforward.
Right, one more time. Thank you, David. Thanks. Gonna take a very short break, just 3 minutes.